Imagine managing the most skilled factory worker on the planet. They build complex parts at lightning speed, but they have a catch. Every time they take a break, their memory is completely wiped. When they start their next shift, they have no idea what they were just building, or even where they are. Modern AI coding assistants operate exactly like that worker. In computer science, we call this statelessness. Every time you open a new chat window or switch to a different computer, the AI starts with absolute zero memory of your previous session. To compensate, you have to spend 5 to 15 minutes copying code, pasting it into a new window, and re-explaining the rules of your project just to get the AI up to speed. Because the computer forgets, you are forced to become the message bus. You become a manual, flushy data link, a meat puppet, running context back and forth between different machines. We build software to automate repetitive tasks. Relying on highly skilled human engineers to act as manual thumb drives defeats the entire purpose of automation. So, if we look at this from a system architecture level, how do we get isolated, memoryless computers to work together? We use a protocol. For anyone new to computer science, a protocol is just an agreed-upon set of rules for formatting and passing data. Think of it like a perfectly structured relay race, where the baton smoothly bypasses the human standing in the middle. Our entire global internet runs on protocols, yet in our most advanced AI workflows, we haven't established one. The AI sessions can't talk to each other, so the human is left to fill the gap. Fixing this doesn't require us to invent a magical AI with infinite memory. We just need to build a standardized set of rules so these isolated sessions can leave notes for each other when we log off. That brings us to the Meat Puppet Elimination Protocol, or MEP. It is a text-based, self-enforcing system that relies entirely on tools developers already use every day. The first component is the identity file. By placing a specific text document in the main project folder, we give the AI a set of instructions. When you start a session, the AI automatically finds this file, reads it, and learns exactly how it needs to behave for this specific project. The second component is the Handoff File, a highly structured shift logbook containing 3 specific sections: what just happened, what needs to be done next, and what to watch out for. The structure has one absolute, unbreakable rule. New entries must go at the very top. The newest information is always the first thing the next session sees. The third component is the transport layer. We use Git, the standard version control system developers use to save code, to automatically push these text files from one laptop and pull them down to another. The result is a persistent memory for the AI. We didn't build any new servers or complex databases. It works through simple plain text files, the kind you can open in any basic notepad, and standard Git commands. To see how robust this structure is, we can look at a real-world stress test from April 3rd. 2 different computers updated the handoff file at the exact same time. This created a version control traffic jam known as a merge conflict. In a typical workflow, a structural clash like this crashes the process. The system freezes and untangles the overlapping text. But because we strictly enforced the newest on top rule, the AI could read its own protocol. It looked at the conflicting dates, identified the chronological error, and knew exactly how to merge the timelines together. It stacked the dates correctly, saved the fix, pushed the code, and closed the session. It did all of this without a single human click. Applying a strict structure that the AI can actually understand allows the machine to organize its own history. This provides the mathematical logic required for a stateless AI to reason through an error and fix its own operational failures. This logic scales even further when we consider that engineers rarely use just one tool. You might use one AI ecosystem to brainstorm architecture, a second for formatting text, and a third to write code. To pass context across those different ecosystems, we use a simple conversation URL as the baton. You take a web link from your brainstorming session and paste it directly into your coding session. The receiving AI reads that link, extracts the key decisions automatically, and updates a shared project log. Now, every future session knows exactly what happened, regardless of which tool you used. This creates a single convergence layer. You can route specific tasks to the AI model best suited for the job, and you never have to pay the time tax of re-explaining the project history. The core engineering takeaway here is that highly scalable, reliable systems often run on simple rules and existing tools, rather than massive, complicated new infrastructure. By adopting simple text protocols, you remove the friction of acting as a manual message bus. The context handoffs smoothly lock into place on their own, leaving you completely free to focus on high-level logic. Check the link in the description to explore the NukaSoft open source repository. You can install this identity file into your own coding environment and start experimenting today. As we build more advanced software, designing the invisible rules of communication is just as critical as writing the code itself. Let the computers handle the relay pass. Don't be a meat puppet.